So does anyone have any questions about anything from yesterday? No questions? Okay. So let me get my whiteboard started up. Okay, so for the next couple of days, we're going to be just working hard on getting lots and lots of examples under our belts of how to use Newton's laws. And there's basically two kinds of problems we're going to see. We're going to see what we were doing last time, which is problems where there's a scenario and some, forces, and we have to make sure we find all the forces and then use that to determine the acceleration. And there are sometimes going to be problems where we know the acceleration already, and we then want to use that to find forces, find missing forces. So let me give you an example like that today. So that's a little different to get us started. So suppose we just have, let me see. Okay, so suppose we have a rope. And underneath that rope there is a box. And the whole thing is moving upward. So if we were to draw that, there might be an acceleration vector A, and maybe that's 5 meters per second squared. So I'm not drawing the acceleration vector on the object because I don't want to confuse it with the forces. I generally will draw the forces directly on the object. And suppose we want to know the tension. Tension in the rope. Okay, so that's a fairly typical problem. And maybe this object has a mass of 3 kilograms. So the idea here is that instead of adding up the forces to find the acceleration, we add up the forces which add up to a known acceleration that will allow us to find an unknown force. But the steps are basically the same. Okay, the first step is we have to draw in all of the forces. So someone tell me one force that would be acting on this mass. Anyone? One force. Gravity. I knew someone was going to say gravity. I wasn't sure who's the gravity person, but there's always one person who's like, gravity. Good for you. All right. So I'll draw the force of gravity in there. Now, I should have asked this question up front. How many forces would be acting on this object? We remember how to count the forces? So there should be the number of points of contact plus 1 forces. And how many points of contact are there on this block? 1, right? So there should be 2 forces. So we got one of the forces. The other force then is coming from the contact with the rope. And that force, I like to draw the force just right in the rope, okay? Let me go back a little bit. That force must be longer than the force of gravity somewhat, or else this thing wouldn't be accelerating upward. So, and that force we call tension, okay? So tension is the word we give whenever there's a force in a string, a rope, a chain, something that, you pull it, it becomes taut, and then it exerts a force. And the interesting thing about tensions is you cannot push something with a tension, you can only pull. So you can't, if you're walking the dog, Either the dog is pulling you or you're pulling the dog if the string is tight, but you cannot push the dog with the rope. Okay, so we know there are only two forces. We have two forces, and so we're good as far as the diagram goes. So our next step is write down net force equals MA for each mass. In this case, there's only one mass. And then we do it for each component if the component is relevant. So in this case, of course, obviously, the x components are not relevant because there are no forces in the x direction. So we're just going to do sum of the y components equals m times the y component of acceleration. And there are two forces, tension and force of gravity. Okay, so normally when I am doing the left-hand side of Newton's second law, I list the forces, but I do not put plus or minus signs in yet. Okay, so I just list them or the components. In this case, the tension y component is the whole tension, and the force of gravity y component is the whole force. And so now I just put in plus or minus signs based on the direction. So I get a plus sign for the tension and a minus sign for the force of gravity because the tension is up and force of gravity is down. And that's it. Okay, that's my equation. Now, the next step is solve for unknowns. So let's figure out what we know. We know the mass. We also know the acceleration because the problem gives it to us. And we know the force of gravity because yesterday we learned force of gravity is just mass times g. And we know the mass and we know g. So that means we can directly solve this for the tension. Tension is going to be force of gravity plus m times ay. That is mg plus m times ay. We could even factor out the m and g plus ay. Okay, so now putting in my numbers, we have 3 times 9.8 plus 5. So let's see what we get. So that is 44.4, and then at the end we need to know what the units are. But since it's a force, we know the units should be newtons. So that's how we find the tension. If this thing were descending, now notice, force of gravity in this case, that would be 3 times 9.8, that's 29.4 newtons. So I'm just kind of doing that math for you. But to see, the tension is bigger than the force of gravity. On the other hand, if this thing had been descending, accelerating at -5 meters per second squared, we could have put a minus sign in for a minus sign in front of this 5, and we would have gotten a force that was much less than the force of gravity. All right, any questions about this problem? All right, let's do a similar problem, but let's make it a little more complicated. So I've got a rope, another rope. I don't really need a third rope for what I want to do. And then we'll have a box there and a box there. And maybe this first box, we can call it M1 and say it is 5 kilograms. And the second one, we can call it M2, and perhaps it is more full and it has a mass of 10 kilograms. And suppose that we know that we apply a tension to the top. Oops. And that tension has a size of 200 newtons. And I want to find two things. I want to find the acceleration of each block. So we're going to find A for each block and the tension between the blocks. Okay, so is it clear what we're looking for? We want to find the acceleration of each block, and then we want to find the tension in between the locks. Any questions? Okay, so who can tell me what the first step should be? Yeah.
Finding the points of contact.
Okay, so where are the points of contact?
The tension.
Okay, so on the block on the top, there's a point of contact on the top and on the bottom. So there's 2 points of contact. We should have 3 forces. So that's a good idea. And on the block on the bottom, there's only 1 point of contact, so we should have 2 forces. So good. What do I do once I know how many forces I should have?
You should try to use the Newton's second law.
Yeah, and in order to do that, I want to draw in all the forces first, right? So so let's do it. Let's see how we would draw those forces in. So on the mass on the top, we're going to have force of gravity. So let's call that force of gravity 1. Since I have 2 masses, I have to call the forces of gravity different names. And then there's contact between the block and this rope, and so there's going to be some kind of force there. And remember, it's a tension. The force in the rope is a tension, and tensions always pull. So this rope, when it touches this block, it has to pull away. It cannot push. So this would be the tension. We could call it tension 1. So that's 3 forces on block 1. That must be all of the forces. So we can go to block 2. On block 2, we're going to have force of gravity. It's going to be bigger force of gravity because it's a bigger mass. Let me try that again. And we'll call that force of gravity 2. And then there's also a tension acting on block 2 that is pulling it upward. So that force, we can call it tension 2. Okay, so that's, from my perspective, that's the first step. And those steps that I told you guys yesterday, draw in all the forces. So there we have it, all the forces drawn in. I know, thanks to Ziad's suggestion, I know how many forces on each block. I know there's 3 on the block number 1, and there's 2 on block number 2, and I've found them all, so I'm done with drawing in forces. So what's the next step after I've drawn in forces? Dustin says, would T1 and T2 be the same? Good question. Why would they be the same? Dustin, I'm kind of directing that question to you. You suggested they might be the same. How come?
Because the mass pulling on both of them would be the same. Or is that not right?
The mass pulling on both of them is the same? Is that what you said?
Yes.
Well, I'm not sure exactly what you mean. You might be on the right track, or maybe not. I'm not sure. The masses are definitely different masses. One is 5 kilograms, the other's 10 kilograms. So can you say more about what you mean?
I guess I'm just seeing it in my head that the M2 is pulling down on M1, but in my head it seems to be the same, whichever direction it's going.
Okay. All right. I want to just put a pin in that for a minute. I think you're onto something. Does anyone else have an idea how to go further with that and say why T1 and T2 might be the same? So they are the same. They are the same, and there's a really good reason for that. And the reason is Newton's third law, which may be kind of where you're coming from or why in your mind it's seeming like they should be the same. Because what is T2 exactly? T2 is the effect of mass 1 pulling on the rope and therefore pulling on mass 2. So T2 represents the force of mass 1 acting on mass 2. In this case, it's because there's a rope. In another case, they could be glued together, or there could be a hook or something. What's T1? T1 is mass 1 pulling down on mass 2. So this would be a case where the T1 and the T2 are the same, but they would be different from this tension up here. They're different because this tension on top is between mass 1 and, my hand or whatever is pulling up on the rope on the top. That's not in my picture, but there's another side of that rope on the top, and there would be a 200 Newton force in that side of the rope as well. But whatever T1 is, T2 should be the same because of Newton's third law. So good. If we recognize they're the same, you're getting a little ahead of me. I was going to surprise you with that. But if we recognize that they're the same, then we can call them just both T1. So we don't have to sort of artificially worry that they might be different once we understand that they have to be the same. Good. So we have, but I don't want to just call them T because I already used T on the top. So I need different symbols for those. Okay, good, good, good. So now, once I've drawn the forces in, what's the next step according to what we said last time? Anyone have notes? What we did last time? Katerina?
Split it into the X and Y components.
Yeah, so we want to write down Newton's second law. Do you prefer Katerina?
Yeah, Katerina or Kat, either is good.
Okay. So we want to write down net force equals ma for each mass. So the net force is on mass 1 equals m1 times a1, and the net force on mass 2 equals m2 times a2. And we would, in general, split this into x and y, but I'm just going to split them into y, in part because I don't have room to really say anything about x, and in part because there's no forces with x components. All right, great. So let's look at mass 1. We've got 3 forces. They are T, T1, and force of gravity 1. That's it. I just list the forces on the left-hand side. And then I let the picture, and this is why it's so critical that we get the forces in the picture and that we get them pointing in the correct directions. I use the directions of those vectors in my picture to determine the signs. So the T by itself, that 200 newtons, it's upward, so it gets a plus sign. And you don't have to write a plus sign in front of it, but I'm just doing it to sort of remind you and remind me that I did think about it and determine it should be positive. And for T1, it points downward, so it gets a minus sign, and the same goes for FG1. Okay? So that's my Newton's second law for mass 1. Now let's go to mass 2. Here we have T1, and we have force of gravity 2, and on the right-hand side, M2 times A2. And the signs are such that the T1 should be positive because it points upward when it acts on mass 2, and force of gravity 2 points downward. So we get a minus sign for that. And let's go through and see what we know. So we know the tension T, it's given in the problem, 200 newtons. But we do not know T1. I mean, maybe we know it, but as far as I can tell, we don't know it. Force of gravity 1, do we know it? Well, yes, because we know the mass, and we know the force of gravity just mass times g. So we know Fg1, we know M1. So there's two unknowns in the equation. On the other equation, T1 is still unknown, but we know force of gravity 2, we know mass 2. So what we have is we have two equations, but we have three unknowns. The unknowns are T1, acceleration 1, and acceleration 2. Let me underline our unknowns in green. Okay. So does anyone know how you solve two equations with three unknowns? The answer is no. Not only do you guys not know it, but I don't know it, and nobody knows it. Okay, nobody on Earth can solve two equations with three unknowns. This is sort of a fundamental fact in algebra. You need as many equations as you have unknowns. So if we have three unknowns and only two equations, what should we do? Cross this problem out, move on to the next one? No, we shouldn't do that. What we need to do is we need to find another equation. That's what it means. If I have two equations with three unknowns, because nature knows what the acceleration is going to be. So if I have too many unknowns, it means I need to find more information, not that there's a problem with the universe. Anyone have an idea of any equation that would relate T1 and A1 and A2, or any combination of those? Ordinarily, when I get to this point in the process, we have four unknowns. We have T1, we have T, which we know, and we have T1 and T2. But Dustin, with a little bit of foresight, recognized, hey, wait, actually T1 and T2 are really the same. So that you could think of that as an equation that T1 equals T2. You know, T1 equals T2. That's sort of a third equation that reduced our number of unknowns. And we have something similar going on with the acceleration. Anyone have an idea about the relationship between A1 and A2? All right, which acceleration do you think should be bigger, mass 1 or mass 2? Ziad?
So actually, I was kind of confused about the way, I guess, acceleration is applied here, because I thought that since we're not really, like, the way I'm just thinking about it is that we're not really going anywhere, if that makes sense.
Well, why do you think we're not going anywhere?
Because we're just hanging from, like we're just hanging an object. Um, I don't know, like I'm kind of confused about that.
Okay, yeah, the picture does look a little bit static, But if we would add up mass M1 and M2, M1 is 49 newtons and M2 is 98 newtons. So the total weight of these guys is 147 newtons, but we're lifting with 200 newtons. So this actually will go up because we're lifting. It's like we're pulling the rope and we're lifting it up because we're pulling with a harder force than the combined weight of those two masses. So this thing will actually be moving upward.
Okay. Thank you.
So if it's moving upward, I guess what I'm looking for here is that the accelerations A1 and A2, they should really be the same. Don't you think? I mean, they're going to be moving together. So it doesn't matter they're connected with a rope. If this rope is like a spring or rubber band, so it's stretchy, then the accelerations wouldn't necessarily be the same. But if it's kind of a, you know, just a normal rope, then it's not going to really stretch. And so if mass 1 moves up 1 meter, mass 2 has to also move up 1 meter. So they're moving together. So my second equation that I'm looking for is A1 just really equals A2. And going forward, we will probably assume that most of the time. But I didn't want to assume it the first time around until we had a chance to discuss it, because otherwise you might later on, you know, just get confused about that. So really, I should just call this A and call this A. My eraser's not working. Okay, M2A. So if I do that, then we really have two equations with two unknowns. Now, two equations with two unknowns, I'm positive you know how to solve that in general, in math class. In math class, it looks something like x plus y equals 3 and x minus y equals 6, and you were trying to solve for x and y. Okay, so in physics, it's more complicated because we have all of these symbols, but the structure is the same. How do you solve this math? How do you solve this thing in math class? There's kind of two most common ways that we learn in math. Does anyone remember how to solve such a system? Ziad?
I think here you could do something called, if I remember correctly, it's called addition. So it's basically like you can take the top and add it to the bottom. Like you have plus y and you have minus y, so then you can combine those and you'd eliminate them. And you can do the same thing with x, except you'd have 2x, and then also with 3 and 6, you'd get 9.
Yeah, so that method is called elimination. And yeah, exactly. We can add the equations or subtract them, or add 2 times the first equation with 3 times the second equation, or whatever we need to do in such a way that we cancel one of those unknowns. And that's called elimination. That's the one most students don't like as much. What's the other way? Does anyone remember the other way that you usually learn that almost all students like better? Elise?
Is it called substitution?
It is. Can you explain what that is?
So like you would solve for one of the variables and then plug it back into the other equation.
Yeah, exactly. So then the other equation loses that other variable. Yeah, that's exactly right. So we could do either one of those here, but I'm going to argue that elimination is better. And the reason it's better is because we have minus T1 here and plus T1 there. And just like what Ziad saw with the y's, having a plus y and a minus y, that if we add them, they will cancel, that's going to happen here as well. T1 minus FG2 equals M2A. What I do is I just stack the equations on top of each other, and then we see that the forces that come out of Newton's third law, the T1 and the T1, those are an action-reaction pair. They are just going to cancel, and that's not just lucky for this problem. That's going to happen almost all the time when we have multiple objects. There will be forces between the objects, and those forces between the objects are just going to cancel. Okay? So even though you may like substitution better because it's less thought in math class, it's sort of like you don't have to think at all. You just know I'm going to do substitution, I'm going to solve for x and plug it in, and it's a well-defined task. It turns out that elimination mathematically is less steps and a little bit easier when we're dealing with Newton's second law. So what do we get when we add them? We're going to get a t minus fg1 minus fg2 equals m1a plus m2a. And we can do some simplifications. For example, fg1 is really m1 times g, that's our formula. And fg2 is really m2 times g. And on the right, I have two terms with a, and I want to isolate a, so I'm going to factor the a out. And then the last step would be just to divide by m1 plus m2. And when we do that, it cancels out on the right-hand side. So finally, our acceleration is 200 newtons minus 5 times 9.8 minus 10 times 9.8. Or if you already worked out the size of the forces of gravity, you could just put those numbers in there. And then that's divided by 5 plus 10. So let's see what we get there. .53 meters per second squared. Okay, so that's the first part, to find A. Any questions about that? Okay, so real quickly to recap before we go on and find the tension. We got a problem which basically was just a picture and sort of one piece of information about an external force, the tension, and information about the masses. Then we had to draw in all of the forces. We write down Newton's second law for each mass. And then what we get is a system of equations. Really, ultimately, it boils down to two equations with two unknowns once we can think about it for a little bit. Then we add those equations to eliminate one of the variables, and we solve for the variable that remains, which in this case is acceleration. Now, I have to go back and solve for the second variable, the second unknown. Just like if I solved this equation for x first, I would go back in and plug it in and then solve for y. Here we found acceleration. So I'm going to go back into one of my two master equations, or not master, but original equations, and solve for the T1. It doesn't matter which one I pick, but I'll pick the equation on it. So I'll take this equation, and I'm just going to move over here to get a little extra space on this slide. And we have T1 minus FG2 equals M2A. So T1 equals FG2 plus M2A. That's going to be M2G plus M2A. That's going to be 10 9.8 plus 10 times 3.53. That is 133.3 repeating newtons. Okay, so let me kind of talk through what's happening with the tension here. That's T1. We apply a 200 Newton tension on the top. And the tension in the middle, T1, it sort of adapts itself. If you look at this number, you have 133.3 newtons. That's exactly 2/3 of this 200 newtons. So 2/3 of this force goes through to the second mass. And if you find the net force on mass 1 coming from the tensions, it's T minus T1, there's only 66.7, or 1/3 of this tension essentially remains on mass 1. Essentially, the tension in the middle adjusts itself so that the 10 kilogram mass gets twice as much force as the 5 kilogram mass. That's basically the bottom line. That's what happens. It gets twice as much because it's twice as big, or twice as massive. Okay, any questions about this problem? All right. So let's do one more example that involves a tension, but it's going to involve an additional complication. And then we can take a break. Maybe we'll even take a break in the middle of this. Okay, so what we have here is a table that has a pulley on the end of it. And then we place a box on the table and another box or block hanging below. So we have an M1 here, M2 there. And we're still doing frictionless problems, but we will learn how to do friction after this example, okay? Now I want to find the acceleration of each mass. And the tension in the string, okay? So it's really one piece of string that wraps around from M1 to M2 via the pulley. Now, the pulley, normally, the first time we see a problem like this, we just ignore the pulley. We say the pulley has no friction and it's massless, or it's so small that its mass is not a factor in this situation. And then we actually, if we were in the in-person class, we would do a lab and actually replicate this example. And we would see in the lab that the pulley is very, very low friction and not very massive, so it's okay to ignore it. So we're going to ignore the pulley itself, not think of it as sort of a mass 3. And we want to find the acceleration and then the tension in the string. We should think of this string as going really directly from M1 to M2, and we don't care, it's not between M1 and the pulley or M2 and the pulley, but just between M1 and M2. And then we can draw in our forces. So first of all, we're going to have a tension in the string, and it's going to be the same tension in both strings, because it's really one string. Then on mass 2, we had only one point of contact, so we have two forces. There's going to be a force of gravity 2. And on mass 1, there's 2 points of contact, the front where the tension is, and the bottom surface, which creates the normal force and friction if there were friction. And then we have a force of gravity 1. So we're going to solve this time with no numbers. In other words, we're going to be getting a formula that if you just tell me what m1 and m2 are, I can tell you the acceleration. Okay? So it's going to be purely symbolic. Counting points of contact, I have 1 point on mass 2, so 2 forces, that's good. Mass 2, I have 2 points of contact, so 3 forces, that's good. So I'm sure now that I have all of the forces. And once I have all the forces drawn in, we now go in and write down Newton's second law for mass 1. Net force on mass 1 equals m1a. I don't have to call it A1 and A2 necessarily anymore. Or, well, we'll talk about that in a minute. And over here, we're going to have the net force on 2 equals m2 times a. And on mass 1, I split this into the x and y directions, but on mass 2, I don't care about the x, right? I only care about the y. So on mass 1, we have tension as the only force in the x direction. And the acceleration is entirely in the x direction. So the whole thing, the whole acceleration is a. On mass 2, we primarily care about the y direction, right? So we have a t, and we have force of gravity 2 equals m2 times a. Now here's where it gets a little tricky, and this trickiness is going to be there anytime we have a pulley, okay? So let me point something out. Mass 1 is moving to the right, so it's moving in the positive direction, and I would say that the acceleration should be a positive number. But mass 2 is moving downward, and because it moves downward, I would say that its acceleration should be a negative number. So there's an inconsistency in my calling the two accelerations the same. If A1 is 2 meters per second squared, then A2 properly should be negative 2 meters per second squared. So I have one of two options. I can really call them different things, A1 and A2, which will kind of complicate the problem by introducing more unknowns. Or I can do the following trick. So I'm really trying to push you toward this trick. What I do anytime I see a pulley is I draw an arrow, a bend arrow around the pulley, either clockwise or counterclockwise. In this way, it's kind of clockwise. And I just decide I'm going to call that direction the plus direction. So what does that mean exactly? It means instead of thinking about plus versus minus as having to do with being up versus down or right versus left, I'm thinking of my plus sign as having to do with any force that tries to bring my whole system in the direction of motion. And any force that's going against the direction of motion would be getting a minus sign. So in this case, the tension on mass 1, it is trying to bring mass 1 in the direction of my blue bending arrow. So it gets a plus sign. In the case of mass 2, it is the force of gravity that is going in the direction of my plus sign. So the force of gravity is going to get a plus sign. Now that is not intuitive. That's not the way we've been doing it all along. The tension, on the other hand, acting on mass 2, is trying to bring mass 2 up. It's trying to bring it against the blue arrow, so the tension gets a minus sign. So what I want to do, once I have written out my equations with the signs, I want to just stack them. I'm just going to copy this and paste it. Move the copy over here. Okay, so I'm going to stack them up and add them. When I do that, just like before, we can see the t and the minus t cancel. And that would not have happened if I had called up positive and down negative for mass 2. And what's left on the left-hand side is just force of gravity 2. And on the right-hand side, we have M1A plus M2A. So I can simplify by calling force of gravity 2 M2G. That's just using the formula that force of gravity is mass times G. And on the right-hand side, we can factor out the A. So we have A times the quantity M1 plus M2. And finally, A is just M2G over M1 plus M2. There is my formula. Now, sometimes when you have a formula and you don't have numbers, it can be hard to know if your formula is right or not. So one thing you can do is you can kind of test it to see if it makes sense with special cases. For example, what if M2 is very, very large compared to M1? So that is, what if M2 is a bowling ball and M1 is just like a paperclip? So if that's the case, we should expect M2 to fall pretty fast. If it's really heavy and M1 is not very heavy, then M2 should fall pretty fast. How fast? Close to G. It should be almost in free fall. And we can see that in our equation. If I basically ignore, do that with green, if I basically ignore M1, then we could see the M2s cancel and we should get an acceleration of G. So that's something we can check. If it's not totally computing with you right now, maybe think about it, watch this little section again later and see if it makes more sense. Or ask a question now. On the other hand, what if M1 is the bowling ball and M2 is the feather? So if M2 is very, very light, we can ignore it on the bottom. And what happens is we wind up with a small number on top divided by a very big number on the bottom. And that's going to be a very small acceleration. That's what we expect if we have a bowling ball on top and a paperclip or a feather on the bottom, that the acceleration should be very, very small. So that's a way, if I have a formula, I can check it by looking at special cases. You can even just make up numbers and put them in, like 100 kilograms and 1 kilogram, and see if the answer fits your intuition. All right, any questions about this example? Okay, so let me just quickly recap what's new in this example, and then we'll take a short break. So what's new is we have this pulley. And when we have a pulley, it changes the direction of a rope. And that can confuse us with regard to the signs of things. Okay, these tensions should be equal and opposite in some sense. And so what I do is I define the direction that I expect the motion to be all the way through the system as plus. And any force that's trying to move the system in the direction of that arrow gets a plus sign when I go into my individual equations. And any force like the tension on mass 2 that's actually trying to bring the mass in the opposite direction to this bending arrow, that will get a minus sign. If I do that trick, then I can still always say that the A's are the same, because they're either both moving in the positive direction or they're both moving in the negative direction. Okay, so let's take maybe a 5-minute break, and then we'll learn how to do friction.